Hello, guys, and we are live. So today I have the pleasure of hosting or co-hosting a webinar with Ubiquity Robotics. So we have David and Gaspar from Ubiquity Robotics. I'll let you guys introduce in a moment. And today we'll be discussing about Pico-ROS, right? Trying to explain, what it is, but even before that, how did we get there, which I think is an interesting journey. As usual, there will be obviously some talking, there will be some code and some demo, as we
as always,
and as per our tradition. So I suggest we do a quick roundtable. I think everyone knows me. I'm the host of this webinar series. So Angelo Corsaro, Zscaler CEO and CTO. Julian is a very frequent guest. So
Julian Hock, committer for Zenoh, but also maintainer for RMW Zenoh for us too.
And we have our friends from Ubiquity Robotics. So David.
So I'm David. I'm the CEO and founder of Ubiquity Robotics. And Gaspar?
I'm the lead firmware developer now, currently here.
Okay, cool. So I think we have some stuff to cover. I would say that we get started. How about that, guys?
Few slides.
Yeah. And by the way, guys, let's keep this interactive. I mean, we like it to be as such. So if you have something and you want to pitch in, don't hesitate. And I usually make small pauses for that. But in any case, don't hesitate to pitch in if you want to say something. So it's really a few friends around the virtual table discussing and presenting cool technology.
And online also, don't hesitate to post questions in the stream.
Right? Absolutely. So we'll be answering them either as they come, some of the people not talking, or at the very end of the webinar. Okay, so let's share the screen and we should be going. So my screen should be visible in a matter of a moment. Let's just give it a few seconds to come up, but I think that should be up on all the different streaming platforms. Okay, so once again, introducing Pico-ROS. And I think it's interesting to understand, how did we get to Pico-ROS, right? Because there was an entire journey. And in the end, the journey is always the most fascinating part in a way. And, the destination for me doesn't exist. It's just from one step to the other, just to begin a new journey. So let's see now landing in Pico-ROS, what other journey will allow us to start. But if we go back a few years, right, I mean, we were raising the issue since, I would say, 2015, maybe even before, because of our experience back then in some massive smart city systems. That back then we could see an increasing number of systems that needed to span and operate from the microcontroller up to the data center. And if you fast forward today, robots are a perfect example of that. Back then, we didn't have so many robotics applications. Most of the robots were fixed robot, not mobile robot, usually expensive robots used in manufacturing and so on and so forth. But in 10 years, the landscape has changed. And this need of being able to run or to have systems that operate from the microcontroller up to the data center has become extremely important, right? So the pain that we were feeling 10 years ago, if we would have not addressed them, it would have been even worse today, right? And again, robots are a very good example because in robot, you have microcontrollers, right? Several of those, especially in complex robot. You have microprocessors. You have sometimes GPUs, or in many cases GPUs. You have high volume data sensors. So are pretty interesting machinery to deal with. And if you are into any kind of mobile robotics application, then you have the challenges of swarm communication, teleoperation, monitoring, and so on and so forth. So back then, there were really no technologies that could address this problem. And this is why, as some of you know, we took the challenge to address this problem, and we ended up designing Zenoh, which is, the first of its kind as a protocol, because it's a protocol that unifies pub, sub, and query. So it allows you to do data dissemination as well as distributed queries. And we found out that the distributed query mechanism can also be used to represent computation. And so, for instance, for those of you that use ROS services, actions, services, because actions are built on top of services, right? ROS services are built straight on top of query. And that makes it very efficient in terms of discovery, in terms of the semantics, scalability, and so on and so forth. As we have always been working in high-performance computing. We knew that support for zero copy and shared memory is quintessential. And so we had support for shared memory and zero copy since the very beginning in Zenoh. I think it was version 0.5 or 0.6, something like that. I don't think that in the ROS ecosystem, we are yet at leveraging the full potential of Zenoh shared memory, but you already have shared memory support, as we will see in the RMW. The other important aspect, so people that work in IT system, right, they think that IP is all that matters, and IP networks, right? Because in the end, most of the let's say regular application run on that. But if you come from embedded system or high performance systems, right, then you know that sometimes the IP stack is not there, other times doesn't deliver the right level of performance. And so when designing a protocol, for us, it was very important to make sure that our new protocol, namely Zenoh, wouldn't have any dependency to the IP stack. And more importantly, we wanted to be able to run at the data link layer, which means we do routing. That doesn't mean that we cannot run over IP. Of course, we can run over IP, but that means that we can run without IP, we can run on serial, we can run natively on Bluetooth, and so on and so forth. Now, this is nice, but something, and I will have a slide that address that in a moment, but something that is even better, not only Zenoh is, can run across this multiple transport, but the same application, as you will see in the demo, right, can use different transport or different link, as we like to call them, because literally they are treated as a link at the other link level at the same time. So I can be an application that talks with serial through serial with another Zenoh application, through QUIC with another, and through Unix socket to yet another, only to talk TLS when communicating, or QUIC when communicating across the Wi-Fi or across the internet. So that's very powerful, and that's something that if you are an embedded system designer, it's quintessential, right? Because other technology often are completely bound and dependent on the IP stack, and so it's up to you then to deal with the things that can't use IP and, for instance, require serial or something else. I'll go quickly because we want to get to Pico-ROS. The other important things is that Zenoh is the abstract protocol, and then we have two implementation of exactly the same protocol, and this is sometimes something that creates confusion to people, right? Because they hear Zenoh and Zenoh-Pico, they say, Zenoh-Pico, there has to be less stuff. Okay, so let me clarify this. So the implementation of the Zenoh protocol that we call Zenoh, yeah, that creates some ambiguity.
Zenoh.
It's built in Rust. So 100% Rust core, which I think is very important because anything that is, facing the outside world, you really want to nowadays to be Rust because of the impact, the positive impact on security. I was listening this morning a podcast, we were discussing earlier during our workshop, and I was hearing that apparently there are now requests, for instance, from the NSA and equivalent organization in the US to have a clear roadmap toward memory safety on system programming languages. There was already a call for arms to move to memory safe programming language like Rust for all software, but now they're requiring a clear roadmap. Otherwise, those languages won't be anymore allowed in anything that is related to defense, to critical infrastructure, to medicine. And if you think about robots, right, I think Rust is
a very
also
important part,
correct.
Yeah.
But then inside the robot, right, if you have a Rust facade, which is what Zenoh allows you to do, the microcontroller, of course, we have been looking at Rust, but the world of microcontroller is still dominated by C. This is why we have a C implementation of Zenoh called Zenoh-Pico. Mm-hmm. And this Zenoh-Pico, it's a full protocol implementation. So there is wide interoperability. Zenoh-Pico can do peer-to-peer. Zenoh-Pico can do everything that Zenoh-ROS can do, with one exception that I'll explain in a moment, that has to do with the topology that are supported for peer-to-peer. With respect to OS supported, well, obviously Zenoh-ROS runs on anything where you can have ROS running, including platform like QNX, for which we have ported all depending grades like Tokyo to QNX, and we support it as a company. And for Zenoh-Pico, well, I mean, it runs on pretty much anything you can imagine. And if it doesn't, then it's really straightforward to port. Now, if we look at the topology that are supported, in Zenoh as a protocol, you have no constraints with respect to the topology we can support. So we can do peer-to-peer under the assumption that every peer can directly talk with every other peer, let's say like DDS, okay? But also we can do meshes. And the only difference, meshes like we have here on the top right corner, the only difference between Zenoh, let's say Rust, and Zenoh-Pico is that Pico does not support meshes. Why? Because that would require adding routing logic in Pico, which, I mean, wouldn't make it Pico, would make it a little bit a Pico overweight,
Yes.
okay? That's the main reason. And then obviously we have the software routers. You can play the client role. That means that your communication will be facilitated either by a router or by any peer in the system. Okay, here you have again a slide that visualizes the fact that in Zenoh, application can run concurrently and route across multiple links. Okay, so one application, as we see here on the top, is communicating through serial with this other client that perhaps is running on a microcontroller, then in this specific case, through Unix pipe with another peers and TCP/IP here. And in this case, right, this means that suppose some data published by this client would go through serial to this peer, potentially to TCP/IP here, TLS, then QUIC, and just to, I mean, actually that would, yeah, for instance, and then perhaps down to this router. Likewise, you could do serial TCP/IP, open thread. And that's completely transparent to application, which is nice because your application doesn't need to know how you're communicating. You're still using Zenoh primitives. You don't need to know what is making up the path through which we will route the communication. And that can be made by link that are pretty heterogeneous.
And all the links are set by configuration, right? You don't need to rebuild your application to configure the links.
Yeah. Okay, so performance. We have been showing, I mean, I'm always reticent to show performance that we have measured. This is why I was showing performance from a paper that was published a couple of years ago. But the problem is that in a couple of years, we have doubled performance, okay? So these are numbers that I've run a couple of weeks ago, and on nothing special, just my laptop, okay? Again, all the tests for these are included in the distribution, but we are now hitting more than 10 million messages per second with small payload, 8 bytes. And the other nice things is that if you look here at the throughput, okay, there is not a mistake. This is in gigabit per second, and you have several hundreds of gigabit per second. That's on the same machine, because by default, now Zenoh will transparently use some shared memory optimization to communicate also within the same local machine. So the kind of bandwidth that you can get is insane, okay? And here, then, what is creating the limit is actually the bandwidth of the actual hardware. Okay. And in fact, for 64 kilobyte, the peak is 410 gigabit per second, which is just, yeah, but that's the advantage of having shared memory. Okay, so no, Zenoh was out. The dragon, was out of the egg. Okay, people started liking it, and in the robotics community, there were lots of challenges that people were experiencing with DDS that was currently used for many systems. And one of the problems, I think, was especially due to the fact that if you take DDS and try to use it in a mobile or wireless environment, I mean, you're stretching it into an environment that it wasn't designed for, okay? And the main problems are tied to the fact that multicast doesn't work well over Wi-Fi. And if multicast isn't there, that starts getting problematic in terms of scalability for DDS. And the other aspect is discovery, right? Because discovery in DDS is very verbose. It was designed for fixed networks, right? Resourceful systems. And that doesn't necessarily, and highly, I would say, symmetric system, doesn't necessarily map to the kind of application that roboticists were trying to build today. So sometimes ago, I think it was now 2 years ago, there was a study done by the Open Robotics and Intrinsic, evaluating the different protocol available on the market and trying to identify which among those could actually best serve the ROS community. If you have not read this report, I highly suggest you take a look. Maybe we could even post the link in the chat if you don't mind.
Yeah.
And the report is, I find it quite nice because it goes through all the problems that were faced by robotics application. It also looks at the deployment that people wanted to have, and they were foreseeing for the next generation application. And then they gather all the key requirements for essentially the ROS2 ecosystem. And they did a comparison of the requirements versus the feature, and Zenoh came as number one protocol for with respect to how we could serve and address the requirements of this robotics application. And so, besides that, the other nice things that, for which we were flattered and surprised, was that the community was asked, which protocol do you want to have next in ROS? And actually, the majority of the votes went to ROS, which was to Zenoh, of course. Yeah, of course, went to Zenoh, which was quite flattering for us. As a consequence of that, it was decided to implement Zenoh RMW. That was a collaboration between Intrinsics and Zetascale, right? And as of Gilded Caillou, right, our dragon woke up with a nice kilt, right? Zenoh RMW actually was delivered already at the ROSCON in Odense.
Yes.
And then we took 1 year to bring it to tier 1. So It's not only available, it's tier 1. And it's the first non-DDS tier 1 RMW in ROS.
In Gilded Caillou, for Gilded Caillou. But still, it's available for all the live distribution, right? RMW Zenoh is available for Humble, for JZ, for Rolling, of course, and for Gilded.
And again, as I say, those that know me knows that we should never rest, right? We are never done. And in fact, tier 1 was not a landing place, it was a departure. And since the tier 1, we've already done quite a few improvements.
Yes.
And there are some pretty cool things in store that will unveil one after the other, okay? So once again, it's not the destination, it's yet another departing point.
It's a first big step.
Exactly, but it was a pretty massive step. Yeah. And I think it was achieved fairly quickly, right? For sure, faster than any other tier 1. Okay, so we were supposed to talk about microcontrollers. So in all of this, we have the Zenoh RMW, but how about microcontrollers? And here we go back to Zenoh-Pico. So now that you have Zenoh RMW, what do you do on microcontroller? Then you could say, you look at Zenoh-Pico, it says, okay, it has best-in-class performance on microcontroller, lowest resource usage, and with the availability of RMW, right, more and more people wanted to leverage Zenoh-Pico on microcontroller, which actually you can. And you can explain how to achieve that. But perhaps, it's not necessarily the most convenient. So let's try to understand how we can do that and why it's not necessarily the most convenient approach. And then let's see how also that problem can be addressed. So, Julien.
Yeah. So as you probably know, ROS2 has a modular architecture with your application based on the RCL API, either RCL CPP, RCL Pi, RCL Java. And those API are sitting on a common RCL layer, which implements all the high-level concepts like actions, parameters, time, console logging, and so on. But at the very bottom, you have the RMW layer for ROS middleware, in which you may have several different implementations. So most of them are based on DDS, Cyclone DDS, Fast DDS, Connex DDS, and the new one, of course, RMW Zenoh. So in the main ROS architecture, RMW Zenoh is based on Zenoh in Rust, using the Zenoh-C API, and it's implemented in C++. So now, if you want to communicate, to make any Zenoh application to communicate with this stack, you need to follow the exact same pattern that we used in RMW Zenoh. So what is this pattern? How do we map ROS to Zenoh primitive inside RMW Zenoh? First, we have an encoding to use, right? And in ROS, the usual encoding was, of course, DDS CDR. And actually, for RMW Zenoh, we made the choice to keep this encoding, even if the performance are not optimal. But the benefit is to keep the same code generation path, right? Because there are already all the tools to parse all the messages, service, actions, and generate some IDL, and even from IDL generate all the serialization code.
And then if we were to update our bridge, it would also allow to have again interoperability with DDS-based RMWs.
Yeah, yes, because the bridge is also, well, we used to have a bridge from ROS to DDS to Zenoh, and it uses the same CDR encoding, indeed. So that's for the data part, the payload of your application. Now, with regard to the primitive, the ROS publisher and subscriber are naturally mapped to Zenoh publisher and subscriber. And as Angelo mentioned, the service and client are mapped on Zenoh queryable and querier. That's relatively simple. And then you have all the actions and parameters that are anyway implemented on RCL layer. So it's not up to RMW Zenoh to implement this. That's on the upper layer to implement actions and parameter in RCL layer. And the last point is about the ROS graph. In ROS, you have a full ROS graph which is maintained, which allows to discover all the nodes that are running in the system, their types, their publishers, their subscribers, their services, their actions, and everything. For this, everything is based on Zenoh liveliness token. The Zenoh liveliness token is something very lightweight and very reactive. It's just a string, a key expression that we know how we name it in Zenoh, that is declared by any application, and that is tied to the session liveliness, right? It means that as soon as the session is become disconnected, any subscriber to the Zenoh liveliness will get notified that the liveliness token is gone. So in this way, using a certain pattern in the liveliness key expression, we can discover nodes, we can discover publishers, services, and whenever the session is disconnected, we know they are gone, so we can clean up all the ROS graph. So that's the way RMW Zenoh is implemented.
Right, and this is essentially the details that if you want to have a Zenoh-Pico application or a Zenoh application for that matters, interoperate with ROS2, you need to understand and deal with, right?
Yeah, exactly.
Which is,
So, and all those details are written in the RMW Zenoh repository in a design documentation page. And actually, you need to just follow this design if you want to make a native Zenoh application to interrupt with RMW Zenoh. And that's exactly what the Ubiquity Robotics team did with Pico-ROS, right? It's to implement this design on top of Zenoh-Pico. So you need to use the same key expression mapping that RMW Zenoh. I mean, when you have we will see just after in a slide what is this mapping, but there is a certain mapping to follow from the ROS topic name to the Zenoh key expression. You need to use the same data serialization, CDR. The similar attachment in RMW Zenoh, there is, in addition of the data, there are some metadata which are attached as an attachment. It includes the sequence number, the timestamp, and a unique publisher ID, which is a GID. And if ever you want to participate to the graph cache, you need to declare some liveliness tokens. Mm-hmm. Now that it's not necessarily mandatory to participate to the graph cache, I mean, you can subscribe and publish without declaring a liveliness token. It's just that your publisher and subscriber won't be shown when you do a ROS2 topic info or something like this. And for services, of course, if you want your service server to be for a client which can wait on your server, you need to declare a liveliness token for your server. So that's the global way to interrupt with RMW Zenoh. In detail, for the mapping of key expression, it's a little bit complex, but you have this mapping, which is explained in the design document. For a fully qualified name, so a topic name with a namespace as a scope, and for a certain domain ID, you have a mapping which is first chunk in the key expression is a domain ID, then the fully qualified name, then the type name, which is the type in C++ format with column as separator, and then the type hash, which is quite a complex hash, but which reflects already the content of your data type structure, and which then allow to not have mismatch between different topics.
And again, the domain ID so domain ID and eventually the ROS namespace, would be prefix of your chat. The domain ID is really, in a way, a legacy of the DDS-RMW, right?
Absolutely.
That needs to be there. But yeah, that doesn't bother Zenoh either. Yeah.
Doesn't bother Zenoh either.
Okay.
But there are some users using different domain IDs, so we need to have a mapping to.
So essentially, this can be done, but you need to get into the details, right? And sometimes, you can do it, but it's not maybe necessarily the most convenient way. So the question is, how about making it easy, right? Wouldn't it be great if we could leverage the fact that we have a very lightweight protocol like Zenoh-Pico, and then how about having on top of it something that provides a lightweight framework with ROS2 abstraction that we can use on microcontroller, and is in fact much lighter than anything that was there before, usable, right? Because all of a sudden shields all the details. And that sounds too good to be true, but that is Pico-ROS. And, I will let David and Gaspar talk a little bit about Pico-ROS.
Yeah, so that's essentially what we did. I don't know if Gaspar, you really want to add anything?
No, I think the presentation was pretty good.
I think the presentation is pretty good. And I mean, the way that we looked at it is we sat there and said, look, building robots, you want to add peripherals to your robot. And whenever you add a peripheral to your robot, you always wind up having, this is a sort of example of what that architecture might look like. You may have a data interconnect with a computer. Typically, that computer has a whole bunch of payload code, robot management tools, and so forth. You may have a motor controller. You may have some nav sensors and a payload sensor and so forth. And whenever you add a peripheral on a robot, you always wind up adding little bits of code on the computer, like a payload sensor node or a node to drive your motor controller, or a nav sensor node. And wouldn't it be great? But those nodes that you put in and those drivers that you put in to drive all the peripherals make the whole system non-hermetic. And what that causes, because you've got a non-hermetic system, you can find yourself in driver hell, where conflicting drivers and other problems can cause issues with assembling your robot and making it easy to build. So we said, well, wouldn't it be great if, and that affects the scalability of your design and the cleanliness of your design and the ability to make it easy to put your designs together. So we said, well, wouldn't it be great if instead of having drivers on the computer, you were able to put a small piece of code on each sensor, motor controller, and so forth, and those devices would directly publish and subscribe topics. So if you could jump to the next slide, Angelo, that'd be great. And that's what we envisaged when we were thinking about Pico-ROS. Could we put a small piece of code? That piece of code would directly connect with the data interconnect, and you could then make your design more hermetic and a bit easier to use. And the route we chose, as Angelo described, was taking Pico Zenoh and implementing RMW Zenoh on top of it. And we've decided to open source that, so that's available for anyone else who also wants to do that. We've put that design subsequently on motor controllers, and we've designed robots with it. You can see one of our robots here. I don't know, is that visible on the live stream? But one of our robots.
We can
here.
Let me make it appear. Hold on a second. I need to switch streams, but we can make that happen. We can make that bigger.
Yeah.
Okay, there we go.
Yeah. So that's what we've done with this robot here. We built, the first peripheral that we did was a motor controller like this, with a microcontroller on it that contains Pico-ROS on it. We've used these motor controllers to build robots like this. This robot is now available for sale, and even bigger robots like this one behind us all use Pico-ROS on the motor controller to directly publish and subscribe ROS topics and enable your system to be assembled in a hermetic way. In addition to releasing this hardware and releasing Pico-ROS open source, we've also actually released a sort of template motor controller design or template PCB design so that other people can build PCBs with the same form factor and basic sort of layout and connection type and everything else, so that if they wanted to integrate, if they wanted to build a peripheral that would integrate with other similar types of peripherals, they could do so. So that's all available as well. So we have both software and hardware being released open source, available for people to use. And I think we're going to do
some demo.
And I think we're going to do a demo. We've got, so we are Ubiquity Robotics. I'm right now sitting in our lab in Slovenia. Meanwhile, Julian is in France. And we have this robot set up with a Pico-ROS based motor control. And we have Pico-ROS running on this robot connected to a router in the cloud, with Julian also having a Pico-ROS based joystick there. And Julian is going to be able to, I think, drive that robot around.
Yes, exactly. So, well, just a quick look on this. So it's just a ESP32, right? ESP32S3 dev kit, and to which we connected a little joystick, right, with just 4 cables, one for the X-axis, one for the Y-axis. So Pico-ROS is running here. It's configured to use the Wi-Fi and to connect to a Zenoh router, which is deployed in the cloud, right, on a host which is actually running in Frankfurt.
Yeah, and I'm gonna share my screen so we'll be able to also see that part. Hold on a second. We still want this visualization here. Okay, great. So here
we have some tooling to show exactly.
So this is where the router is running. So if we connect our ZC2.
So ZC2 is our tooling which allows to view all the interconnectivity of a Zenoh network, right? So what we can see here on the top is the router in the cloud, which is running on roscon.zenoh.io.
Yeah.
To this router, we have 2 connected nodes. The first one is, of course, this ESP32. The second one is the tool itself, right? And we can see at the bottom 3 nodes. The first one in the middle is the router, RMW Zenoh router running in the robot. And in this robot, we can see there are 2 nodes, one connected in blue, which is actually, I think, the motor's driver, also running Pico-ROS, right, and connected via serial.
Yeah.
So we have a serial connection here between Zenoh-Pico and RMW Zenoh D router. And the second node, it's a traditional ROS node connected over the loopback, which is subscribing to the joystick and changing remapping the topic to be CMDVEL, right?
Yeah.
So it's just mapping the joystick command to CMDVEL. And with this now, I can just move the robot. So here, from front, I'm sending some joystick command into the robot. And you can see it's quite reactive, right? If I move now, only a few milliseconds of delay.
Yeah, and we're going across, yes.
You can keep going, Julian. That's actually...
Yeah, because if you don't see completely the table, go. Okay.
I just want to make it full, right?
Okay,
it's a very nice robot. I don't want to make it break, but...
it's pretty resilient. So.
It's pretty resilient with these, and these robots were designed to be a very cost-effective design, so that we can offer these to our customers at reasonable rates. But yeah, so you know, and it all works flawlessly is the thing, with extremely low latency, despite connecting over a very long distance. So the performance has been really great.
From Paris to Frankfurt, and then from Frankfurt to Slovenia. Yeah,
correct.
So that's quite a big trip for just a few
even over one serial line in between.
That's right.
Absolutely, one serial line.
Yeah. So, and again, this goes back to what we were explaining. So, but I want to see some code, guys. Otherwise, you know, I'm unhappy.
Yeah. So I think let's see if I can share my screen, because I think I've been kicked out.
While they're bringing that up, we're going to be designing all of our robots going forward based on this framework. And all of our robots are going to be using, all of Ubiquity Robotics' robots are going to be using Pico-ROS in the core. And we are also trying to cultivate groups of sensor makers to include Pico-ROS. So we've already signed up several sensor makers to include Pico-ROS in their sensor design, so that then you'll have sensors that you could just plug into the robot, have a hermetic design, and so forth. And of course, we would like more people to join us in making Pico-ROS peripherals and Pico-ROS devices and Pico-ROS items and items that can plug into robots and so forth.
Yeah.
So we're going to be releasing routers.
Yeah, it would be great. And by the way, I mean, I think it's worth giving a little bit more. When you were ready to share, I'm ready to. Yeah. So it would be worth to give a little bit more context also. When Zenoh RMW arrived, right, as I mentioned, there were quite a few people that wanted to start using Zenoh-Pico on microcontroller interoperating with ROS. And, we were socialized with some attempt of doing that. But among those, Pico-ROS is the best one, right? So I think as the best design, it's very lightweight.
It's very lightweight.
And this is, as a company, what we plan to support and what we will recommend. Okay, so I think that's, it was very, very, we were very, very pleased to see that, because, I mean, we were to the point that we said, okay, if nobody does it, we'll do it. And then, it was there and I said, oh, and it looks great, right?
Yeah. Very well designed.
Yeah. So this is why, we were very happy about this collaboration, and this is what we, would recommend to everyone to use.
So there is a repository that Gasper actually made online, which is inside the Pico-ROS organization. It's a Pico-ROS example, and here you have this example with ESP32 joystick. And so let's have a quick look to the code, because it's really nice. I mean, of course, you have the constant to connect to your Wi-Fi to set up the channel of communication for the joystick, for the X-axis, Y-axis. Some deadbands in order to avoid the noise, right, when it's low. Where you need to connect to, so that's actually will be the IP address of the RMW Zenoh router or any Zenoh router you want to connect to, right? Yeah. So here it's a local IP address, but we change this to be ROSCON Zenoh.
Yeah, and so you have the option also to connect through serial to a router.
Yeah, exactly. Yeah. Yes, that's what is used inside the robot for Ubiquity Robotics. And here we start with the ROS code. First, declaration of a node, which is quite trivial. You just declare a structure with the name of your node, and the declaration of a publisher. And here you declare the topic name, a ROS type name, and a host type hash. And here there are some very smart macros that allow to define all the type, but allows also to generate all the serialization code, which I will show you, which are in another file. And actually, Gasper already included a lot of pre-existing standard types that are ready to be used, right? You can use.
There is even tool now, tool supported to parse the IDL files and build this macro header files for including.
That's great. That's great. I didn't know that. That's you're going very quick in adding features, and that's very nice. Yeah.
I mean, just to make some comment here, maybe, because how I came to this is because I'm pretty new to ROS, and when I start investigating this, I start seeing all the type support and all the build system for type support. It starts hurting my head, basically.
Yeah.
To start bringing this into my C project in embedded. So then this macros idea came about because I had before experience with this X macro type system. It's pretty good, basically generic system in C. So it can.
So we're getting some questions. Do we want to answer the questions now, or should we leave them until after the code?
Well, let's answer one, because I think there is one that is quite important, because Arduino, it's a super popular platform.
Yeah.
So does this supports Arduino? Because Zenoh-Pico does, right? So
yes, I mean, from Pico-ROS, we support all the hardware that Zenoh-Pico currently supports.
So great. So you can run on Arduino, ESP32, Zephyr, FreeRTOS.
Yeah.
It's. I mean, it was written for. Our target was STM32, but we deliberately designed it so that it was hardware agnostic. So in principle, it can run on anything, right?
Yeah.
Arduino can run on STM32.
Exactly. I mean, even design of Zenoh-Pico originally is done nicely, so we could keep this. I mean, it's
on larger platforms as well in principle. So even if you just didn't want to run everything on a more powerful platform, you had some small thing that you wanted to do, you could use it there, right?
Mm-hmm. So, and then once you declared your publisher on your node, let's jump to all the initialization, the main code. So there is nothing very, very fancy here. You have, of course, you need to initialize all your communication for your board, right, with the ADC channel, it's a Wi-Fi. And we have the initialization of Pico-ROS, just a single Pico-ROS interface initialization with the Zenoh mode, which can be either client, either peer, and the connection to the router. And here we have the router address. Then some initialization of interface. So that's an asleep to wait for the connection to the router to be established. And just a single line to initialize the node. So that will make all the declaration of the node, including the liveliness token to declare the node in the graph cache, right? And the declaration of the publisher. So here we have the declaration of the publisher with also liveliness token and with the initialization of the structure. And then we can just have a task that will run all the publication. And the task is relatively simple now. Just get the information from the ADC connectivity, perform some transformation to apply the deadband %, and then we create the data type. So here we can see the equivalent of the complex data type that exists already in ROS with RCL CPP or whatever, which is here in C. And we can just build full data here with a header with timestamp, and then a sequence of two floats, which is the x-axis and the y-axis for the joystick command. Serialization, just one line to serialize in a buffer, and publication, just one line to publish. And we are done.
Yeah.
Relatively simple.
So the Zenoh-Pico code, it's pretty simple. It's pretty because most of the code is ESP32 configuration essentially. Yeah.
Exactly.
So that's pretty neat.
I would even recommend people interested to look at the examples. Pico-ROS repository, we include there a bunch of examples which are actually even smaller, but they are usually I use them to test running code on Linux, on Unix system.
Yeah.
But there is like all the, let's say, I try to make examples for all the functionality that we kind of support.
So here you refer to all the examples which are in this
Pico-ROS software, yes,
repository.
Yes. You can
and here in examples, yes, there are indeed a bunch of examples, starting with, of course, the simple talker listener.
Yeah, it will be even less lines of code, I mean, to understand without initialization of embedded side.
And even what is very nice is that also parameters are supported. You implemented all the parameters.
Yes.
Which
we needed that for our motor controller, basically. So
our motor controller generates full parameters, and you can fully tune the motor controller. So
use the ROS tools.
You can use the ROS tools to tune it. So you send a command vel message to the motor controller. You can send a command vel message to the motor controller,
or at least parameters message, or
parameters, and you have dynamic reconfigure on our motor controller. So those were all necessary things that we needed to do in order to make it work. And that's all supported.
Cool.
Very good. Yeah. So I think that's it for the demo. We shown everything we have, and
which I think was a lot, right?
Well. Yeah.
Okay, so there were a couple of questions, some remarks. So I mean, there is some remark from Ingo, right, which is saying, to be fair, the complexity of ROS type
generation system. Yeah,
we agree.
We completely agree, Ingo. I mean, it's no doubt, right? I mean,
and I think actually there is some of the complexity that ROS has in itself behind type generation that stems from the fact that you want it to be independent of the middleware, right? Anyway, so I think indeed, I mean, nothing is free, right? But in this respect, here you have something that is trying to be as efficient in time and space and line of code you need to write, right? Because we can assume it's one middleware, and
Yeah.
Okay. So, yeah, go ahead, David.
Yeah, that's the trade-off. And then Ingo, again, we may want to port our CLC with its executor to this as well. So yes. Great comment.
Well, I would say that to be very compact, the solution right now is just good enough, right? There is no need of an executor, just one thread, which is good enough just for a small sensor to publish some data. Indeed, if you want to build more complex application based on Pico-ROS, an executor will be nice. But for microcontroller, do you really want to have more complex application on a microcontroller?
Yeah,
there could be some use cases.
I mean, our vision was really that, because obviously we're building, Ubiquity Robotics is building, we build standard robot types which you can get on our website, but we also build custom robot types for a lot of customers. So for us, what motivated us is we wanted to be able to build custom robot types quickly and easily, and so that making things hermetic really matters, because what we want to be able to do is, and what I think other robot builders want to be able to do, is take a series of sensors, plug them together on the robot, and for everything to come up, for the topics to be there, for us to be able to introspect them and use all of the ROS tools in order to be able to build whatever application it is that we want to do. And that's what motivated us, and what we hope will motivate other people. And we obviously want other people to join us and participate, and for it to be a healthy part of the ROS community. Right?
Also, to maybe give some, let's say, example. Let's say in our motor controller, we currently use some topics also that are not handled by ROS layer, let's say, which is the update topic of firmware and some other things, let's say. So, I mean, even it's not problem to support like ROS and topics, and don't pass data through the ROS system, let's say, if you need to, in the same application.
Yeah.
Okay. So we have another question, actually. Let me. Okay, I can also show the question to the stream. Is it possible to detect disconnection from microcontroller side? So Zenoh-Pico has connectivity event. So the short answer is yes. Do you guys expose this connectivity? There are liveness tokens.
Liveness tokens are perfect use case for this, right? As soon
as
you have
exposed at the Pico-ROS level.
Yes.
Okay.
Yes.
So then,
it's exposed via the graph cache, right? If you subscribe to the graph cache,
you want to know it from the microcontroller side. Yeah. You're not subscribing the graph cache. So
yes, microcontroller side in Pico-ROS currently we don't handle this disconnects or check with them. So there is still, let's say, some features that we plan to develop with community, but it's a question also. I think we will need to have more input also from, from other people and see what the requirements are.
And by the way, on our side, the connectivity event on Pico are not yet exposed, and they are part of our roadmap for the next quarter. So you will have it before the end of this year.
Yes.
And then you will be able to expose that. Yeah.
Okay.
Because
for now, currently, I think there is only this reconnection mechanism that automatically reconnects, basically, and it works. Let's say on ESP32, I see it working, reconnecting. Let's say if there is failure in network or.
But so for those that are interested, I'll share the RFC with connectivity event, because there is no special API today. It's just a subscriber to a special key. But we are going, as we did for if you have it ended, as we did for liveness token, we are going to express a full a first-class API to deal with connectivity event, because that way will be a little bit user-friendly, and the same API will be available across all language bindings, including Zenoh-Pico. Yeah, so Julian is posting the spec of connectivity status.
Post in the chat. Can I?
No, post it there and then I'll repost. Yeah. Okay, thank you. Here we go. So that's what we currently,
Yeah, then we will need to add the support of detecting this event and like closing subscribers, reopening or reiniting.
Correct. Yeah. Cool. Let's see if there are, because I mean, the experience is that when we are about to say bye, you will get a couple of questions. It happens every time. You say, okay, thank you. I stop the stream and a question pops up. So we're going to count up to 10. Anybody that has more questions, like
last
9.
chance for
Exactly.
a question.
Exactly. And while counting in my mind, let me thank you, Guy, for joining this webinar.
And for developing Pico-ROS.
Of course. I mean, that was my last point, right? So it was great. We should do some more. Keep having some regular update for our user base. And again, I mean, great job with Pico-ROS. As I said, that was what we were hoping to see, and it came. So you see, my smile is up here, right?
Well, it's been wonderful to collaborate with you, Angelo, of course, and I hope that we can continue to do this and really try to push the field forward. For me, it's not just about, this is, as you said, just the starting point, and we think that the way in which people should be building robots in the future is plugging bits of hardware together and it kind of just working. And the Pico Zenoh is what enables that, and Pico-ROS is going to be a component of that, we think. So yeah.
Cool.
All right.
So thanks so much also to you guys. It was also a pleasure to working with your software and integrating it in our robots. So
thank you.
Yes.
Okay,
right.
cool. And thank you everyone for for being online and following us. See you next time.
Thank you.
Bye.